Well, hello, welcome back. Today we are taking a look at how do we determine the actual formula of a compound based on empirical information or based on information about mass or quantities or something else that we know. So using the concept of the mole is still a part of what we are doing, especially molar mass. But now we're going one step further, as opposed to percent composition, where we're literally just trying to figure out, well, kind of what are the relative amounts of two elements that are present. From this particular sequence of videos, and I think it's at least two videos, we will take a look at how do you actually determine a chemical formula from information that you can derive in a lab. So with this, first thing you need to know is what the term empirical formula means. And that's what this process is called, these math problems. The term empirical simply means something that you can determine basically via lab data, that you can determine from observation or measurement, something along those lines. So when we are doing empirical formulas, or formulae is actually the technically correct Latin pluralization of that word, but when we're doing empirical formulae from these sorts of things, we're trying to figure out what something's formula is. Not just like, oh, it's 5% hydrogen, but is it H2 or is it H1 or is it H3? Trying to actually figure out what the little subscript numbers are. So in this little kind of visual over here on the left, hopefully you can kind of see what the difference is between an empirical formula and a molecular formula. So in the end of the percent composition one, we took a look at what the percent composition was of glucose, C6H12O6, and we also did sucrose, C11H22O11. Sorry about my awkward writing on there. And we did both of those and realized they had the same percent composition. And the reason is because they have the same empirical formula. So take a look. Here is the actual molecular formula, the size of the molecule as it exists. But this value down here, an empirical formula, is the simplest possible ratio of atoms, sort of like reducing your fraction down. So if we've got 6 to 12 to 6, you can reduce all of those. Those are all even numbers, right? We can divide each one of those by 6, and we get an empirical formula, a simplest possible formula of CH2O. 1 to 2 to 1 is the actual ratio. By the way, this is why sugars are called carbohydrates. That's the whole reason behind there, is we take a look at even sucrose, which is another type of carbohydrate. 11 to 2211 can be simplified down to the exact same empirical formula, 1 to 2 to 1, or CH2O. CH2O is the empirical formula of this particular compound. Again, an empirical formula, it can be determined by simple lab data or lab analysis, and it gives us the ratio, it gives us the subscript numbers rather than just a percentage by mass. So with this, here's how we actually work this out. Now, these are kind of some multi-step problems, so calculator, patience, all that kind of stuff. It'll take me a little while to walk through these, and so that you can kind of see what they are. But this is the kind of data that you get. So you found some sort of a new compound, and you find that it contains 3 elements: carbon, hydrogen, and chlorine. Those are the only 3 that are present. And then when you do the measurement out, you have the number of moles of each one. Now, I've given you moles in this one. Normally, you'll get grams. I just put moles in here to sort of eliminate a step, to sort of eliminate the grams to moles conversion. But we'll see some of the other ones with moles here in a second. So if I've got 0.78 moles of chlorine, okay, what do I need to do? The goal here with an empirical formula, I'm going to look back at this one, is I want to figure out what the simplest possible ratio is. Is it 1 to 2 to 1? Is it 1 to 1 to 2? Something like that. I just want to find out the simplest possible ratio of these two things. And by looking at this, when I'm in moles now, I'm sort of at that ratio point. This isn't a mass, so I don't have to do anything too scary with this, but it's really hard to tell what the formula is. 156 moles of carbon, sorry, I gotta read that, and 0.39 moles of hydrogen. If I had given you some really easy to see numbers, if I'd said that there was 2 moles of chlorine and 4 moles of carbon, this is not the same problem, and 6 moles of hydrogen, it would be really easy to reduce this down, right? You could just reduce it and say it was going to be, all right, I can go this, I can do this, I can do this, Cl C2H3, right? I could reduce down those ratios and get to that simplest possible ratio. If I had a slightly harder set of moles to it, you might still be able to see what it is. So if I had 0.25 moles of this, 0.50 moles of that, and 1.00 moles of this, now that ratio is a little bit harder to see. It's still there, but what is that ratio? Well, in order to do this, we would simply literally go, well, it's one of these and that's two of them. You probably can see it in your head. The math is you divide each one by the smallest number. So this is the way that we simplify these things. You don't even think about it with easy formulas because you do it so fast. But if we do this, 0.25, do this divided by 0.25, and do this divided by 0.25, take the smallest number of moles and divide each of those by that small number, the ratio a lot of times will just kind of like magically appear. So 0.25 divided by 0.25 is 1. 0.5 divided by 0.25 is 2. And 1.00 divided by 0.25 is 4. And we can get our ratio really easily by this simple mathematical trick. So here's what it's going to be with numbers where it's a lot harder to see what they are. But it's the same basic math. And that's what I'm going to appeal to you, is that when it's big numbers, y'all know how to do it. But we forget what the math trick is that we're doing when they're not obvious values. So again, the trick. When you're in moles, all you have to do to simplify this ratio is to divide by everything, divide each one by the smallest number. In this case, our three values right here, our smallest value is 0.078. All I'm going to be doing by doing this is, again, trying to see if I can get that ratio to sort of appear and make it a little bit easier to see. So that's an easy one. That's a 1. 0.156 divided by 0.078 is 2. You may or may not have known that. I knew that, but I don't know. You guys would know. I'm simulating. 0.39 divided by 0.078 is 5. And again, all I did was just divide it in there and divide them out to see what they are, because that's what's going to tell me what my ratio is. So I know that these are combining in a ratio of 1 mole of this combines with 2 moles of this and 5 moles of that. So when we write our empirical formula, those mole ratios become our subscript numbers. And so you've got to do that last step and write the formula. This particular empirical formula would be Cl, you don't have to write the 1, C2, again, this is carbon, and there's 2 of them in there, 2 moles of it, and then hydrogen and a 5. So you don't have to worry about, like, is that really the order that they come in? Don't stress about it. Whatever order they're given to you in the problem, you can just list them straight off. So this right here would be the empirical formula of our compound. That's not necessarily its real formula. May be some multiple of this, like in the sugar example. But I know that these combine in a ratio of 1 to 2 to 5. And that gives me a baseline to deal with for my empirical formula. So let's try another one here. Okay, this one's a little bit more challenging because now you can see in this one, I'm not giving you moles, I'm giving you grams. So the first thing that you have to do with these is convert grams to moles. The only way we can do that reducing phase is if we are in moles first. So you kind of set it up similarly. I'm going to take my chlorine, 71.65 grams of chlorine, and I'm going to convert grams to moles. How do I do that? Molar mass. So molar mass of chlorine, if I find it on here, is 35.45. 35.45 grams of chlorine is 1 mole of chlorine. And then I'm going to hit equals there. I'm going to set up the same one. Carbon, 24.2 grams of carbon. I'm going to do the same thing. Molar mass, grams goes down here, moles goes up here. That's a C, sorry. And then again, I'm finding my molar mass on my periodic table. For carbon, it is 12.01. This is how I convert these to moles. And then the last one that I need to do is hydrogen, 4.07 grams of hydrogen. And I'm going to do my conversion. 1.01 grams of hydrogen equals 1 mole of hydrogen. So you can kind of see how I'm setting this up on the paper, where I've got like three little wonder fractions, 1 for each element. It's definitely easier to kind of do these little ones vertically rather than horizontally. It seems to fit on the paper better, but you do you. Make yourself happy. So Now, what is it? 71.65 divided by 35.45. And the answer to this one is, 2.02 moles. And that's chlorine. 24.2, I'm doing carbon now, 24.2 grams of carbon divided by 12.01 grams of carbon is 2.001 moles. That's a point there. Again, we're going to keep our I'm kind of being floppy here a little bit with sig figs, but don't, and this is one of the few cases where it doesn't actually matter that much, as long as you keep some extra digits around. I'm kind of keeping with my 2 decimal place rule that seems to work really well with these. And then the last one, 4.07 divided by 1.01 is 4.03 moles. So this is hydrogen, this is carbon, and this is chlorine. Excuse me. So with these, all we have to do now is simplify. What's our mole to mole to mole ratio? What combination do these guys make? Pardon me. Ooh, that's cold from this morning. But you can probably see this one, right? This is one of those ones where you don't even need to do this actual like simplification step because you can see it. It's a 2 to 2 to 4, which you can simplify out. If you want to do it the long way, you divide everything by the lowest, this number right here, 2.01. That's actually the math that you're doing in your head to kind of see what this is. But it's a ratio of basically 1 chlorine, this is 1 carbon, and this is 2 hydrogens. In empirical formulas, our ratios here always need to be simple, whole numbers. If you get something funky like 2.01, that's close enough to round it. I'll show you some examples in the next video. What happens if these don't come out as really nice, neat numbers? So, last step, again, write your empirical formula as a formula with subscript numbers. This would be Cl1, C1, H2. So slightly different empirical formula than the previous one. So our steps are convert grams to moles for each element, and then divide by the smallest number of moles. And this is what helps us to simplify that ratio. It's simply a math trick, is all that is. I think I've got one more to do today, and then this video will be done. All right, so last one, similar version of this. How do we do empirical formulas if we're not given mass, but we're giving percents instead, percent composition? Very common way that you would do a percent composition analysis like in the last video, and then you'd go one step further with your percent composition to figure out the empirical formulas. All right, well, what do we do now? Well, our compound contains 32.63% of phosphorus, and the remainder is oxygen. All right, 32.63%. Well, how do I put percent in a math like this? I don't know how to do a percent to moles composition. Here's the trick. There's always a trick, right? You know me. There's always a trick. If I have exactly 100 grams of the compound, again, nothing is given to us. It just says percent composition. I can have whatever size I want. I could have 200 grams. I could have 500 grams. I could have 1,000 grams. I could have 1 gram. But I'm going to make it really easy on you. Let's pretend like we have exactly 100 grams of this particular compound. If I know that it's 32.63% phosphorus, 32.63% of 100 grams is 32.63 grams of phosphorus. So you can literally, in these kinds of problems, you can just literally translate those over and say, hey, all right, instead of percent, I'm just going to call those grams. It's sweet. I love easy tricks. It's so nice to have those happen like that. I'm going to do my same thing where I have to do my grams to moles conversion. Phosphorus has a molar mass of 30.97 grams is 1 mole of phosphorus. So I can figure that out. All right, so 32.63 divided by 30.97 is a number, right? Okay, well, it's 1.054-ish, something like that, moles, MOL of phosphorus. Okay, great. Now what? Well, we're missing the other element, right? So we got to deal with the oxygen. So how much oxygen's in there? Again, basic little piece, little trick. If you know that this thing is 32% phosphorus, the remainder has to be oxygen. So you just do 100 minus 32.63 to give you your remaining mass. Again, that's the remaining percent, 67.37. Oops, hold on, sorry. 67.37% grams is oxygen. Again, we're literally saying, all right, if we know that I've got a 100-gram sample and 32 of those grams are phosphorus, then I can simply subtract. Sometimes you can just read the problem and find that information that's in there. All right, we're going to do our grams to moles step again, like we always do. Grams to moles, grams of oxygen, moles of oxygen. One and only one mole weighs 16.00 grams. There we go. And figure this one out. 67.37. I wish my 6 button worked. 67.37 divided by 16 gives us this number, 4.21 moles of oxygen. So this is one of those ones where it's not quite as easy to kind of see how this is. It's not a 1 to 4. This number is too close. It's not close enough to 0. Like this one, I'd be comfortable rounding that to 0. But this is not a 1 to 4 ratio. So let's do our actual math part and see what happens here. 1.054 divided by 1.054 and see what we get. Well, I know that one's 1. So what's 4.21 divided by 1.054? There we go. This is now equal to 4. Okay, so we are close enough. It's fine. I'm not too worried about it. And I got like this, 3.999. The point I'm trying to make here is don't just assume you can round these off. I'll show you in the next video where you definitely cannot. So don't assume that you can round these off. As long as you're keeping your kind of 2 decimal places in here, it should work itself out pretty well. And again, 3.99, I am pretty comfortable with rounding 3.99 to 4.0. I am not comfortable rounding 4.21 down. That is too far away. So what would our ratio be here? Well, our ratio would be PO4, like it's a phosphate maybe. I don't know. So that's how you do empirical formulas. So we're going to come back in part 2 of this little video here, which will do some of the more difficult ones. So I would suggest right now, take a moment, digest this. You got to do the couple of steps to get empirical formula. So we covered what an empirical formula is. It's the simplest ratio. And then we kind of covered what the steps are. You have to get to moles. So a lot of times you're doing a grams to moles conversion first, but then you're trying to figure out what that simplest mole to mole ratio is within this compound. So a lot of times our trick is to divide by the smallest number to see if we can simplify that ratio and get them to nice, even whole numbers. That's how we do empirical formulas, and it gives us an insight into the actual chemical composition. I'll see you in the next video in a little bit. Have a good one.